Okay. Welcome to Math 70. So you guys have been talking with a partner about why we need to know how to solve problems. So can I get some volunteers to share what they and their partners said about this? Volunteers? Yes, sir.
To help have guidance, like in life, come across with a problem, and then you learn to solve it, and then you pass it on to other generations.
Ah, okay. So to have guidance. So if we're all faced with problems in life, and if we, learn how to solve them, you can pass that guidance on to future generations. Okay. What else? That's good. That's it. Everybody said the same thing. Yeah.
Survive?
To survive, right. Right, I mean, it's a pretty elementary question, isn't it? I mean, it's not supposed to be this, revealing, problem solving, I never thought about why that's important, right? Right, but it's something that we do every day, right? In fact, humans have, it's arguable that humans have evolved to have everything they have and be who they are because we're the best problem-solving animals on the planet, right? We have the biggest, most active brains. I don't know about most active, but not the biggest, but the most capable brains. We can use our arms and legs. We have thumbs, right? And we've solved so many different problems, right? Okay, so it's really, really important to know how to solve problems, okay? The book, right? So now if you look at the handout that I gave you, our book claims that people in many professions need to know how to solve problems well. Do you agree? And for your planned profession, what kinds of problems might you need to solve? Okay. So I want you to take another couple of minutes to talk with your partner about, I think we all agree that you need to solve problems based on what we said before, but talk to your person, tell what you think you're planning to do, and talk about what kind of problems you might need to solve in that discipline. Does that make sense in that profession? Okay, go. We're kind of quiet. So does anybody want to share first of all, share with me what your planned profession is, because I'm interested to know, and what kind of problems you might need to solve. Does anybody want to volunteer? I can pick on you. I remember your name, Chris. Why don't you guys? I'm trying to think, whose name do I know? Why don't you tell us? One of you. You don't both have to share, but if you want to.
I was just related to where I work right now, which is
Okay.
an after-school program.
An after-school program? Okay.
Yeah, we're just talking about working with kids. The most important thing is diffusing the problem before it escalates.
Okay.
So things get heated between kids. Just diffuse the negativity. Like, all right, let's get fit. Don't fight over a little thing.
Okay. So you're saying that a problem with working with children is maybe they don't know how to solve problems together.
Yeah. So
Right.
You have to step in and show them.
Sure. And so you have to step in to kind of help them figure that out. Okay. And do you want to share what you?
And from my side,
Is that mine? Yeah, go for it.
from my side of the, I would like to become an illustrator at some point, and so one of my biggest concerns is that the market is so competitive because
Okay.
there's so many artists out there.
Sure.
Not only that, but after art school is really expensive.
Yes.
And so they have to deal with all of that. That's another problem. And so it's just a multitude of problems all across the board.
Okay.
And
Sure.
also drive.
And also what?
Drive
Drive.
to do things.
Yeah, is that a problem?
It can be.
It can be. Keeping yourself motivated. Does anybody else share that problem? I think that's a very human thing to do. I think that's actually one of the reasons that we have solved all the problems that we have as far as, you know, how do we get around, where do we live, and all that stuff, because we're sick of putting so much effort into those things, right? Having to go out and hunt ourselves. So we solved problems and said, oh, these people can grow food for us, and we'll go to a store and buy it. That'll work, yeah. Okay, anybody else? Let's have one more set of people share. Whose name do I know? Okay, I'll pick on someone from last semester. Imri, how about you and your partner group?
I'm a political science major,
Okay,
and so I'm thinking what to do with that now. But one of them is solving conflict between power struggles. So
okay,
you know, people, yeah. So
okay.
I'm an industrial art and illustration major,
Oh,
so I guess the biggest problem is like appealing to consumers' needs,
ah, okay. So what do you mean exactly?
like product design or whatever. You have to find someone who wants that
Okay,
or needs it.
right.
Otherwise, it's useless.
Okay, good. That's a really good thing. How do you figure out what people need and want, right? So that you can market things the best. Okay, great. So did everybody find that you are going to have a profession where you're going to need to solve problems? Yeah. Have you learned any techniques for solving problems? Yeah? Can anybody think off the top of their head of a technique that they might use to solve? If you think about specifically about the profession you're going to be in and the problem that you talked about, what kind of techniques might you use to solve problems? Yeah.
Like breaking the problem down into smaller pieces so it's not as hard to tackle.
Okay, very good. So you take the problem and you say, okay, this seems crazy. Let's think about what the little pieces are that, I can deal with separately. Very good. What else? Yes, sir.
Having experience and a mentor who's gone through it and has a better idea.
That's a really good one. Right. Having an experience or a mentor, getting suggestions from someone, right? I think in this situation in our math class, I'm the mentor, right? You're the mentee. I can share with you my experience, my knowledge to help you along problem-solving process. Anybody else want to talk about? Okay. Well, we're going to spend this first chapter all about problem solving, talking about ways to solve problems. And we're going to be looking at math problems, but you can obviously use these techniques for all kinds of problems in your life. Okay, and we're going to outline some really particular things. And then throughout the semester, most of the work in this class is problem solving, right? Meaning I'm not going to say here's a formula, do 18 problems of the same thing, like an algebra class might be. Things might seem like every problem seems a little different here, right? And so one of the main goals of this course is to kind of help you develop some problem-solving techniques, to learn some new ones and develop the ones that you already have in order to carry on, right? It fulfills the quantitative reasoning requirement for transfer, right? So in here we're going to reason, meaning, grapple with things, solve problems with quantities, okay, in that realm, right? And obviously there are things that you can reason with for the rest of your lives too. But we're going to talk mostly about quantities. But I hope that you find that the things that we talk about can extend to other parts of your life. The other thing I want to say is that I'm not the only person who's going to have ideas about how to solve things, right? One of the reasons I really like to teach this class is because students come from so many different backgrounds, and they're backgrounds that are different from what I have done academically. And so often you guys have really good ideas to put towards things too. Okay, so hopefully we can learn from each other. Okay, so in that vein, what we need to do now is solve a quick problem, and this is a pretty easy one. There are 27 students here in the class, and I want you to get into groups of 4. How many groups will there be? And can we get 4 in each group? Almost. How many groups of 4 can we have?
6.
Okay, because 6 times 4 is 24. And that leaves us how many? 3. Okay. So this is what we're going to do. And 7 groups is a good amount. I'm pretty sure I have 7. Let me just double check. Hold on, sorry. 7 groups. Good, that's what I want, 7 groups. Okay, so you need to get into a group of 4, but there can only be one group of 3. Okay, so I'm not going to say 3 or 4 because I really want most of them to be 4. Okay, so with your partner, perhaps, join another set of partners. Okay, go, and then I'll talk about what we're going to do. And let me know if you're challenged in this, solving this problem of finding 4, 3.
I was making, yeah. So how long do you think it's been? So like.
Okay.
Maybe it's trying to
Okay.
sell these.
Sure. Okay, well, I can't do that right now.
You do 4. Sorry. Do 4.
I just realized you don't have the All right, we're going to stop for a second. Okay, so wherever you are, just pause. And so why don't you tell me what something people did in their group to kind of attack the problem. I don't want you to tell me about your specific problem and its solution, but when I asked you to work together, what did you do in order to, what were the methods you used to try to help each other solve? What did you do first? Yeah.
I made a chart.
Say that again.
I made a chart.
You made a chart. So that's the first thing that you did right away?
Well, I read.
You read it. How many groups read the problem together? People. Did you read it by yourselves? Okay. After you read it by yourselves, or if you did read it together, what happened then? Did you jump right in and say, I think we should make a chart?
We all had kind of different approaches to
Okay. Okay, so you put your approach out there. Did your other group members put their approaches out there? Okay, great. What's that called when everybody kind of puts ideas out there? Brainstorming, right? That's a good way to start a problem-solving process, isn't it? Yeah? What are our ideas about this? What's going on, right? Did anyone, let's back up a little bit. Did anyone make sure that all the group members understood the problem? You did? Your group did?
Well, I read the question out loud.
Good. They read the question out loud. Did you give an opportunity for people to ask questions?
Yeah, I asked what they thought.
Okay. Did anyone feel when they were working like they didn't understand what the problem was? A little bit? Did you ask your group members?
Well, it was easier when we saw a visual. It was kind of hard to, but I think we all just started brainstorming, so
Okay.
it made it easier.
So that made it easier to kind of start. How many groups didn't really work together and just worked on their own? Were you able to solve the problem? You think so? You sure? I'm turning in for a grade. Just kidding. I'm just kidding. I'm totally joking. Okay. What about the rest of you? Did anybody just try to solve it on their own? You did?
We solved it, and then we kind of.
I guess a little bit.
A little bit you did?
After.
And sorry, just a second, Johnny. And so you, sorry, just keep talking.
Oh, so we just kind of, we all kind of dove into it, and
Okay.
then after went through it again
Okay.
together, I guess.
Okay, so you dove into it, you each kind of tried your own thing, and then you got back together, is what you're saying? Okay, that can be a nice way to solve problems, right? I'd highly recommend that actually for this class, right? Because we are going to be doing mostly problem solving, which in real words, teachers call it problem solving or application, but other people see that as word problems, right? Working together in a group might be really, really helpful, can be very, very helpful. But trying it on your own first, I think, is always a good thing, right? Because if you come to a group Nobody likes the person who comes to the group and just wants to rely on the group to do everything for them, right? That's obnoxious, okay? So you want to work on things your own and then maybe get together to talk about the problems, okay? So maybe you've met somebody today that might help. Okay, so I want to now talk, I'm sorry, Johnny, did you want to say something? I cut you off before.
Oh, well, I was just saying that we also guessed, kind of.
Oh, okay,
How to
good.
do it, you know, that was one strategy.
Great. A good strategy is to make a guess, right? Is that where you should end? No. What should you do after you make a guess on something? Test it, right? See if it works somehow, right? In a math question, maybe you can see if it fits with all the rest of, what the problem is trying to say. Maybe you could, if there was an equation or something, which there weren't for any of these, you could go back and plug it in, right? In real life, you need to, sometimes you try something to solve a problem, you test it out, and it doesn't work. What happens when it doesn't work? What do you do with that idea? Throw it out, right? And then just give up and say, I don't know how to do this.
Start all over.
Start all over. Should you use the same approach to the problem? Probably not, okay? That's another reason it's nice to work with a group, right? Because different people bring different approaches to solving problems. Okay, so we had one person draw a chart. Did anybody else draw a diagram? You did. Anybody else draw a diagram? Not every one of these problems probably lends itself to drawing a diagram, but I think if you do get a problem to draw a diagram, that's another good thing to do. Okay? All right. So what we're going to do is we're going to look at two specific problem-solving methods that are introduced by the book called inductive and deductive reasoning. You may have heard of those before. We're going to take a few notes about those things. It's in the packet that I gave you. And then what I'm going to do is I'm going to have you, after we learn about those two things, I'm going to have you get back into your groups and look at those two methods and see if one of those methods help you solve it. Okay? By the way, how many people think they've solved their problem so far? One. Okay, about half, it looks like. Okay, great. Yeah.
So for this packet, is this just for like
These are notes for you.
Okay.
Yeah, I'm not going to ask you to turn this in or anything. You can write on it. I generally like to hand stuff out like that. I can't guarantee that every single time you come to class I'll have something like this. But I do like to use it a lot because that way I can project it. It looks better on the camera. And then also later, if you needed to go back and look at it, what I generally do is take the notes from class and make a PDF out of it and post it on WebAssign. Yeah? So you'll be able to find the notes from the class if you missed it. So anyway, okay. So we're going to talk about inductive and deductive reasoning. Okay. Does anybody know what inductive reasoning is? Have you ever heard that term? Or like, never seen it before? Okay. Anybody have any ideas? You say, did you induce that answer? Right? Where do we use that word induce? Okay.
Labor. Yeah.
Oh, right. For a woman having a baby. Yeah. I was like, labor? Like work? No. Yeah. That's right. Okay. What does it mean if a woman has labor is induced?
Make it happen.
To force to make it happen quickly. Okay. I'm not exactly sure that actually applies to this definition. It's kind of interesting. Inductive reasoning is actually a process of reaching a general conclusion by examining specific examples. Right? So let's say you had a problem that you were trying to reach a conclusion for, right? Maybe here's a question. You know, are all, and you may know the answer to this already, but are all even numbers divisible by 2, right? So you might, if you were going to reason inductively about this, what might you do?
Take an even number.
Take an even number, look at an example, 14, right? I know it's even. Let's divide it by 2. I get 7. Okay, it's divisible by 2, right? So I look at one example. Then I look at another example, 36 divided, right? I might look at some examples of odd numbers, right? And say, if I divide it, is that divisible by 2? No, right? And so I might say, okay, based on that, I've looked at a few examples, and it looks like it's working all the time, right? Then even numbers must be divisible by 2, right? So you draw a conclusion because you've seen something happen, over and over and over again. Does that make sense? Is inductive reasoning is that probably the best way to solve a problem? Do you think that it's the best way to figure out if all even numbers are divisible by 2 is to take a few examples and divide it and it works and say, we're good? Yeah? No. It's not the best way, but sometimes it's the only way. Yeah? Okay? And so mathematics does use inductive reasoning sometimes. And in fact, there are people who have proven or almost proven things using inductive reasoning that have shown that it works for this and this and this and this, but we still don't know if it works for every case. Okay? All right. So we're just going to write that down. You cannot, if you use inductive reasoning to solve something, you cannot be sure that the condition holds for all similar situations. Okay? And because it's not kind of ironclad, right? It's not an ironclad way of showing that something is true. Your conclusion can easily be proven false by finding just one, what we call a counterexample. Counterexample. What's a counterexample?
Proves your hypothesis wrong.
Right, it proves your hypothesis wrong, right? It's an example that shows that whatever you're claiming doesn't hold, right? So it's one case where the conclusion is not true. Okay? Inductive reasoning can get people in a lot of trouble. Can you imagine something, not necessarily in math, but something that people might draw a conclusion from their, from some examples that they've seen or experiences that they've had, and then that's totally not true? Come on, I'm not going to let you off the hook. You guys are here from studying all different kinds of disciplines. You're almost ready to transfer and, get really into something. Think about what you study or what other classes you've taken or what kinds of conclusions humans have made using inductive reasoning. Mm-hmm.
The Earth is the center of the universe.
Okay, the Earth is the center of the universe, right? Who claimed that the Earth was the center of the universe? I hope I know.
Ptolemy?
Yes, it was Ptolemy. And who proved that the sun was?
Copernicus.
Copernicus. Okay, good. So Ptolemy said that the Earth was the center of the universe, right? Or, well, the sun's the center of the solar system. It's not even the center of the universe, right? I meant solar system. So, and so did he use inductive reasoning? Were there examples of other Earths being the center of the solar system that he used?
No.
Okay, no. So I don't think actually inductive reasoning applies to that situation. But thanks for volunteering. Yeah.
Kind of like all stereotypes.
Stereotypes. Good. That's a really good example, right?
You draw like conclusions from like one or a couple of observations, and then you make a general statement. Then there's always like counterexamples that'll prove it wrong.
True. Exactly. You might think, people with red hair are always funny, right? Because you meet 8 people who have red hair and that are funny, right? That does not mean, you can't just say, oh, that's what makes people funny, right? So, but inductive reasoning would make you do that. Yes, ma'am? Gender roles. Okay, good. That's a really good example of a specific stereotype, right? Gender roles. Women should be the ones who take care of the kids at home, right? Or men should make all the money, right? And women should stay home. Those kinds of gender roles, right? You might grow up with that as the norm, right? You might see that in your house. You might see that in other friends' houses. But that doesn't mean that that's, the only roles that those genders can take, okay? Do humans do this a lot? Yes, they do. And I don't want to say that it's a bad thing, right? Because it definitely is. I mean, it's bad in those situations, right? Stereotyping and putting people into gender roles is not really a great thing. But I think it's very natural for humans to do this, right? We learn from our experiences by connecting our new experiences to old things that we've done. And so drawing those conclusions is natural, okay? But what's important is to realize that, you might be, that you're doing it, right? That you might be reasoning something inductively and that it doesn't mean that that's exactly what it is, right? So knowing that you do that about, say, different people, different kinds of people, and realizing that, well, that doesn't mean that it's true, right? That's part of what being human is also true. Okay, I'm going to show you a couple of math examples, okay, of inductive reasoning. Okay, and what we're going to do is, so that's what we'll do. Okay, so the first one is this. Okay, so this is going to jog your memory, hopefully a little bit about some math symbols. What do those 2 lines mean?
Absolute.
Absolute value. So I'm saying that the absolute value of x meaning what? Any number, okay? So x, I'll say that, for any number x. Okay, so this is the conclusion that somebody might come to. The absolute value of x is greater than 0 for any number x. Is that true? Let's look at some examples, okay? So inductively, we may think it's true, right? If we look at some examples. Let's let x be 3. Is the absolute value of 3 greater than 0? Yes. Okay, so check. Let's do a negative number. Is the absolute value of -5 greater than 0? It is, because absolute value is always positive, right? It's always, or it becomes the positive of this number. It's distance from 0 on the number line. Can anybody think of a counter example? 0. Good. But if we let x be 0, the absolute value of 0 greater than 0? No. What's the absolute value of 0? 0. It's equal to 0. Okay? So it's false to say that the absolute value of a number is always positive. Yeah, we have a word for that in math. It's non-negative, right? So that means that's positive including 0. I know. Well, just like any other discipline, if you have a need, you make up a word and define it that way. Okay? All right. Okay, so that's an example of something. Say, if I'm trying to figure out if this is true, I might plug in some things and say, and if I didn't find 0, I might think, oh yes, it is true, right? But then when we see 0, we see that it's not. All right, one more example. How about this one? X squared is greater than x for any number x. So basically what I'm doing is I'm saying if I take a number and I square it, then I get a bigger number, right? So let's look at some examples. 2 squared. Is 2 squared bigger than 2? Sure. Yep, 4 is bigger than 2. How about 3 squared greater than 3? 3 squared is 9, is greater than 3. Yes. But is there a counterexample for this?
What?
1, very good. 1 squared is not greater than 1. In fact, 1 squared is equal to 1. There's another example. What's the other counterexample? 0, right? If I square 0, I also get 0. What about negatives? We didn't do a negative number. Is negative 6 squared bigger than negative 6? Right? Negative 6 squared is a positive 36. Any positive number is going to be greater than negative 6. Okay, so those 3 examples did work, but we only really need one counterexample to say, nope, that's not true. Okay? All right, so that's what inductive reasoning is. Now let's talk about deductive reasoning. All right, does anyone know what deductive reasoning is? Yeah.
It's obtaining a solution from looking at the information provided.
Okay. He says finding a solution by looking at the information provided. Okay. Anyone want to say anything more about that? It's a little general, but I like it. All right. Our book says it's the process of reaching a conclusion. A conclusion by applying assumptions, procedures, or principles. So I've underlined the word procedures because I think it's kind of key here. You know? When you reason deductively, basically what you're doing is you're applying some kind of a procedure. Right? So examples of these might be like formulas, right? That's a procedure. Take this information and plug it into this formula, right? That's a set procedure, okay? So we can say one example is a formula, okay? Another example in math, right, might be something that we call an axiom or a law or a property or a theorem. We're going to talk more about theorems. A lot of these are kind of the same things, right? Or they seem the same. They're not exactly the same. But basically, it's just a statement that, you know, this is true. Like, 4 is greater than 3. Yes, it is, right? And I'm going to apply that to figuring out if, you know, the square root of 4 is bigger than the square root of 3, something like that. Mm-hmm.
About postulates?
Postulates, same thing, yeah. You've taken a geometry class. A postulate, a theory. Postulate generally is something that's proposed. But then if it's proven, it still sometimes is called a postulate. It's just some are proven, some are not. But that's similar to theorems. Laws and properties and axioms are things that actually have definitely been proven, that are not in question at all. Okay, and let's do a math example of using deductive reasoning. Okay, looking at a situation that you might. So here's a statement or a conclusion. The sum of any two even counting numbers is always even. Okay, so that's something that I'm stating. The sum of any two even counting numbers is always even. So if you wanted to try to, reason and see, is this true or not, right? What could you do? Not inductively. Clearly, you could take some examples, right, and add them together and see what happens. But that would be inductive reasoning. And then maybe that's what you do at first, right, to just kind of see. But let's say you wanted to show that this is true for all numbers, no matter what. What could you do? Yeah.
You could look at the definition for what an even number is.
Very good. You could look at what the definition for an even number is. Does anybody know the definition of an even number?
Number divisible by 2.
Good. It's exactly what I said earlier, right? I said, I asked that question. I said, are all even numbers divisible by 2? Well, that happens to actually be the definition of even numbers, okay? So what you could do is you could say, okay, if n is any number, right? If n is any number, then 2 times n is even. Does that make sense? Yeah. Is this number divisible by 2? 2 times n? What would you get if you divided 2n by 2? N. Okay. All right. So you get n. Then so we can maybe agree that 2n is even for counting numbers. I should say any counting number. Sorry about that. Fractions and stuff is not going to work for. Okay. Any counting number. All right. We could also say, well, 2m is also even if m is any counting number. Could be the same, could be different. Just choosing a different variable instead. Okay? Because notice what it's asking me to do. It's asking me to say, look at the sum of any 2 even counting numbers. So here are my 2 even counting numbers. So I'll take 2n and add 2m, right? What happens when I do that? Can I show that this makes an even number? Using maybe some kind of a law or property that you know of? You seem very convinced. What could I do?
I don't know what the name of the law property would be, but you could do 2 times the sum of n plus n.
Good. You know from algebra that this is equivalent to 2 times the sum of m plus n. What property does that? Distributive property, right? Usually we use the distributive property in this direction, right? We take the 2, multiply by the m, then times the n. But in this, it's a property. It could go either way, okay? So we could say by the distributive property. So this property is my deductive reasoning, right? I'm using something that's already established to say, well, this follows that established thing, so it has to be true. Now, is 2 times n plus n, is this even? Yeah, because if I took this and divided it by 2, look, draw a line under and put a 2, I could cancel the 2's and I would get, you know, a number back, right? That doesn't have a remainder or anything like that. It's divisible, okay? We could say which is an even number, okay? This is going to hold for all numbers because I used variables that represent anything, right? I basically said let them be anything. It works. It must be good, okay? So this is an example of what a mathematician might do if they're trying to prove that something is true. Okay, now what I'd like you to do is I'd like you to go back into your groups and look at your group problem again and see if you could apply either inductive reasoning by looking at some examples and seeing if you can draw a conclusion by, you know, looking at those examples and moving on. Or is there some kind of a procedure or a definition or a property or something that you might be able to apply? And you could reason deductively instead of inductively. Okay, and I'll give you maybe about 5 minutes to do this. Okay. And after you see if you can apply any of those things, try to do that and see if you can solve it. You just tried different examples. I think that's. I see. Right. Well, that makes a difference, doesn't it? Yeah. You know, I don't know. I'm not sure. Well, see, inductive would be looking at different examples, right? Did you look at different examples of squares? You drew multiple squares. Oh, okay. Oh, I see. Cool. All right. So that's good. You could also do it deductively. You have any idea how you might go about reasoning deductively for this?
I would say get one square, try it, right?
Okay.
And then prove it right or wrong.
And then keep going from there. Good. That's a procedure, right? It doesn't have to be some predetermined procedure, right? It can be something that you kind of figure out along the way, right? That, oh, this will work. Maybe I could do this. You guys ever play Sudokus? No? Once. There are lots of different ways. It's similar to this, but there are lots of different ways that people use. People have kind of developed their own procedures, whatever. So anyway, a procedure doesn't have to be something that somebody else has given to you. It can can be something you come up with yourself. Okay. All right. Have you guys solved it? You think so? Good. Okay, so.
We tried.
All right.
I tried.
Okay, so did you use inductive reasoning or deductive reasoning? Or 5 minutes. I want to go over a couple of the problems just to talk about what kind of reasoning the group used so that we can become more clear about the reasoning. But before we do that, first I just want to ask, did knowing about deductive and inductive reasoning help you a little bit when you got back to your group to kind of say, oh, maybe if we didn't know how to do this, maybe we could try, let's think of a procedure we could try or something? Did that help anybody? It's okay if it did not. You don't have to like lie. I just wanted to point out that, you know, sometimes when we're working on problems, we get stuck in our ways, right? We're trying something, it's not working, it's not working, it's not working. Having different ideas can be really helpful, okay? So coming back, especially when you're working on your homework, think, okay, have I tried to come up with examples of this, right? Or have I thought about what procedures I might be able to apply? Okay, that's 2 things that you could do. All right, so I've picked a couple of problems that I want to look at, just because they're fairly quick. I'm going to look at problem number 1. Oops, where is it? There it is. Okay, so not everybody has seen everybody else's problems, right? You've only seen the one that you've been working on. Okay, so this group up here did problem number 1. Okay, so you don't need to write this down. So, you know, this is just, the stuff we're doing today is not necessarily reflective of what you'll do on the homework, right? There'll be other types of problems, but you'll use the same kinds of ideas. So you can write it if you'd like. So we're gonna, it says pick a number, multiply by 8 and add 6 to the product, divide the sum by 2 and subtract 3. What can you say will be true about the result in comparison to the number that you start with, okay? And I was walking around and I was asking all the groups whether they were using inductive or deductive reasoning. So this group was doing number 1. Can you tell me, did you use inductive reasoning or deductive reasoning? Both. They used both. What did you start with?
Inductive.
Inductive, yeah? So what they did was they actually did exactly what it says. Pick a number, right? They multiplied it by 8, 6 the product, divide by 2, and subtract 3. What were the numbers that you used?
Where did we start with 3?
3. Okay, so they said 3. They said, let's take 3, let's multiply it by 8, right? That's 24. Then they added 6 to that. 24 plus 6 gives me 30. Then divide the sum by 2, so 30 divided by 2 is 15, and then subtract 3. They took 15 minus 3, and they got 12, right? And they said, what can you say will be true about the result in comparison to the number that you started with? So they started with a 3 and they got 12, okay? So they said, okay, we start with 3 and end with 12, right? Can you draw a conclusion from just one example? No, right? 3 has a bunch of relationships to 12, right? You could multiply by 4 to get 12. You could add 9 to get 12, right? You could subtract 9 from 12 to get 3, right? There's a bunch of different relationships. So then did you try a second number? And what number did you try? 2. Okay, so they said 2. Let's multiply that by 8. That'll give us 16, right? And then they added 6. 16 plus 6 is 22. Then they divided the sum by 2 to get 11. And then they subtracted 3 and they got 8, right? And so they said, okay, if we start with 2, we get 8, right? Do we see a relationship between 3 and 12 that is the same as the relationship between 2 and 8? What is it? Multiplied by 4, okay? So by reasoning inductively, right, they are able to kind of come up with a hypothesis or, you know, a guess. Did you try more then after that to see if it always worked? Okay, they tried a few more, and I think, you know, if you try this 3 or 4 times inductively, you probably, you know, would say, I'm pretty sure it's true, right? I'm pretty sure that you end up with 4 times the number. Then they said, maybe let's do it deductively. So how did you do it deductively?
We made a formula.
They made a formula, right? They said, okay, let's not start with 3 or 2, let's start with x, right? We're going to take 8 times x, right? And then it says add 6 to the product, so plus 6. Oops, sorry about that. And then we're going to divide the sum by 2, right? and then we're going to subtract 3. So they took this, and then they asked me, well, what do we do now? Right? What can you do to this? Can we simplify this? Yeah, we can divide by 2, right? You can factor a 2 out of the front. 4x plus 3 over 2, and then these 2's cancel, minus 3. So you end up with 4x plus 3 minus 3, which is just 4x, right? So if you start with x, you end with 4x, no matter what x is, okay? So that deductive reasoning says for sure, right, that any number you start with, you're going to end with 4 times that number using this method. All right. So I just wanted to show, we actually don't have time to go through any other ones. So keep those in mind as reasoning techniques. Try examples. A lot of times, you know, students will come to me and say, I don't even know how to start this. And I'm like, well, did you try and, you know, did you try to plug some stuff in and see how it works, okay? So inductive is a good way to start, and it might lead you to deduction. Okay, if you owe me the waiver sheet about the video, please come see me and give it to me. And also if you need a syllabus and that waiver, come see me now. Okay, thanks. And we don't have class again this week. I'll see you Monday. There's homework due, I think, on Monday, section 1.1, I think. Pretty sure.